Hey guys, in this video we're going to talk about the magnetic force on a current carrying wire. Now you already know one equation for magnetic force, and that's this one, but this is the equation for the force on a single moving charge. The equation for the force that a magnetic field exerts on a current carrying wire is that one right there. Although the reason why a wire, which has current moving through it, experiences a magnetic force is actually related to that first magnetic force equation we learned about. So let's review that one just a little bit. When you have, let's say, a positive charge moving in a magnetic field, the direction of the force that it experiences depends on the right-hand rule. If you do the right-hand rule for this particular one here, you get an upwards directed force. But the tricky thing with individual charges in a magnetic field is that the direction of the force doesn't stay constant, because as they move, their velocity changes directions. So you usually actually end up with a circle or a portion of a circle. Since after some amount of time, the charge is now, say, moving vertically upward, okay, or up the page in this case, and at that moment, when it's moving vertically up the page, the force becomes inwards, again based on the right-hand rule. When it's at this other later moment, when it's moving, say, that way, the force is now, again, still inwards, all right, but perpendicular in that now new different direction. So it ends up moving in this circular arc because of the changing direction of the velocity producing a changing direction for the force. All right, now what about the current carrying wire? Why does that experience a force when it's in a magnetic field? Well, it's actually going to go back to what we define current as. Current is the movement of positive charge. So think about this wire with a current going through it as having a bunch of positive charges moving to the right. Well, if those charges are moving to the right, based on the right-hand rule, these charges moving to the right experience a force in the up-the-page direction. But unlike the example of the free-moving charge from the left, where it ends up going in a circle because the direction of its velocity changes, and therefore the direction of the force on it changes, these charges can't leave the wire. And so since they continue to move in one direction, as long as that current flows, the force also stays in a constant up-the-page direction. Now, this might be a good moment to remember that actually when we have a current flowing, there's actually negative charges moving through the wire. So the direction of the current might be to the right, but it's actually electrons that are flowing to the left, which you might think would sort of change the answer, like, aha, well, it's negative charges. Well, actually, if you do your right-hand rule, you will again still get that the direction of the force is up the page, because, of course, when you do the right-hand rule, you have to flip the direction at the end of it. So even though it's negative charges moving to the left, the direction of the force on them would still be in the up-the-page direction. And so back to the simple picture. If the current is to the right, using your right-hand rule in exactly the same way as you would use the right-hand rule for QV cross B, you get the force is up the page. Now, if you need a review on that, remember the way that we do the right-hand rule is the velocity is your hand, right? You point your hand in that direction. Then you bend your fingers in the direction of the magnetic field, and the direction of the force is your thumb. All right, using IL cross B, you point your hand in the direction of the current, you curl your fingers in the direction of the magnetic field, and the force is going to be the direction that your thumb is pointing. Now, one other thing that we ought to address with these two equations is how they look very different, and yet they both end up calculating the same thing. They both end up being force. So I want to show real quick that actually the units for both of these equations are fundamentally the same. For QV cross B, charge is measured in coulombs, V is measured in meters per second, and B is, of course, measured in Teslas. Don't worry about how exactly that equals newtons, because that would require us to talk about what a Tesla actually is, and we're not going to get into that in this video. All I really want to show is how QV cross B and IL cross B are the same thing. So back to the point, current is coulombs per second, length is meters. Okay, B is still Tesla. So you can see either way, what you're getting is basically Coulomb meter Teslas per second for both of those equations. So fundamentally, they are showing the same thing, just in two different ways. You get the same result from both equations. So what are some applications of this principle? Well, there are some really basic and essential applications of the force on a current carrying wire for all kinds of things that we take for granted in the modern world. First, simplest example being the motor. Now, this is not, I have not drawn a great motor here. What I'm trying to show is this is maybe the spindle that the motor spins on. So spindle, top and bottom, okay? And you have current coming in, flowing around like this. There's all kinds of coils in a wire, and then working its way out that way. Okay, so if you follow that, that's the sort of loop that I'm showing the current following. Roughly speaking, this is how a motor operates, or at least this is the simplest way of drawing it. Now, a motor isn't just a current. In order for there to be a force on these currents, we need to put it in a magnetic field. Now, the magnetic field being in, say, this orientation, as shown, the various sections of wire will each experience a force. The top and bottom sections of wire, meaning these ones, experience no force at all because the current in those runs parallel to the magnetic field. So there's no force on those sections. And I'm not concerned with the spindles because they are outside of the magnetic field. The left side and the right side, however, will experience forces due to the magnetic field. Now, if you aren't sure what direction those are in, pause the video for a moment and try and use your right-hand rule to predict the directions of the forces on those sections of wire. And here's the result that you get. The right side, the force is going to be in the into the page direction. The left side is going to be pushed out of the page. So if you think about what that's going to do, right, given that we've got this spindle that the thing is able to spin on, well, it's going to spin. Spoiler alert, that's what motors do, is they spin, right? Now, the reason I say it's a little more complicated than what I've shown here is this motor, as drawn, would only spin once, and then it would stop and spin back the other direction. For reasons that we won't really get into. So there's a very clever device inside of a motor, if you want to learn more about them, called a commutator. A commutator causes the current to switch directions automatically, and the purpose of that is to keep the motor spinning in the same direction rather than reversing periodically. So as long as it keeps spinning in the same direction, faster and faster, there you go, that's what you want a motor to do. So a more straightforward application might actually be the railgun. It's also one that I think in a lot of ways is maybe more exciting. What I've shown here is basically you got a battery, and then you've got these two rails. And notice there is a gap in between them. Why is there a gap there? Well, that's where your projectile is going to go. Now, for a railgun, the projectile has to be conductive because when you put it in there, what's going to happen is it completes the circuit. So before, when there was a gap, no electricity could flow because it was an incomplete circuit. One side didn't touch the other. But now that we have a conductive object here in the middle, current will begin to flow. And notice that the current flows through the projectile. For reasons that we will learn about later, the current that is now flowing through this circuit generates a magnetic field in between the two rails that in this case would be into the page. Again, you can do your right-hand rule. If the current is flowing down through the projectile and the field is into the page, that's going to give you a force to the right on the projectile. The force is calculated using ILB, okay, the one we just learned, and ma. Now, let's talk about some of the terms here, though, that may not have been cleared up. What exactly is L? Well, L stands for length, but like which length are we talking about? Like, is this the length? No, that's not the length of the bullet. I mean, it is the length of the bullet, but it's not the length that we actually care about for the purposes of this equation. The L that we're talking about really would be basically the width of the bullet. Okay, it's this distance here. If you were looking at the motor over on the other side, the L would be that right there. So the amount of force depends upon the amount of current and the magnetic field, but also the length of the wire on which it's acting. So if you have a longer section of wire, there will be a greater amount of force acting on it. Okay, so back to the railgun then, the length is, we said, this dimension right here. So how much force you're going to get depends on not just the current and the magnetic field, but the actual physical dimensions of the projectile in question. Now, once you know what the force is, you can calculate the acceleration of it using F equals ma. The next thing that logically follows is kinematics. Oh man, that's a throwback to ancient days. So kinematics, great, wonderful. If we've got a force and acceleration, we can then go through and figure out, I don't know, the final speed given the amount of time that it's in the barrel, or maybe how long it will take for it to travel length, whatever. Sky's the limit, but probably the only necessary simplification to make to these equations is that the initial velocity is, I mean, unless you are running with your railgun, the initial velocity is probably 0. And actually, to be frank, you probably can't run with your railgun. Definitely, you should Google, when you are done with this video, well, look up on YouTube, a video of the Navy's railgun. It's probably technically a coil gun, but if you look up Navy railgun, that thing is amazing. And it's a building. You are not going to be able to run with that. On the other hand, there is a thing called a coil gun, which you can hold in your hand. So that's another thing to maybe look up on YouTube is coil gun. All right, well, that's all I got. That should get you through the homework. So thanks for watching, guys.